Welcome back to Math 1500 Applied Business Mathematics, Connecticut State Community College. Today, in this video, we're going to be looking at solving linear programming problems, and we're going to do it by graphing. Okay, so there's a bunch of information in this top paragraph here. A linear equation where z equals ax plus by is called an objective function. I'm going to come back to this later, but this objective function, we want to either maximize or minimize it according to a bunch of linear constraints. The linear constraints typically come from word problems, and here are some realities that we have. We saw some of this in our previous video. The constraints are going to be several linear inequalities. We're going to try to optimize. To optimize, that means to maximize or minimize. Like in a situation, we might try to maximize revenue or minimize cost, okay, to come up with what's called an optimal solution. A few fundamental theorem of linear programming here, some things to keep in mind. If the solution to a linear program problem exists, it will occur at a corner point. That's huge. So I don't have to evaluate every single point in the feasible region, just the points at the corner, which is very convenient. If two adjacent corner points are both optimal solutions, then all the points on the line segment connecting them will be an optimal solution. That happens occasionally. You'll notice in 3 and 4 that the feasible region may be bounded or it may be unbounded. The problem's not going to do for us in this course. The feasible region is going to be bounded. There will always be an optimal solution. With an unbounded region, you may or may not have an optimal solution. Okay, so let's dive in and look at a couple of examples. The first thing we're going to look at here is number 1, which is just a generic problem. So we'll graph this, okay? I'm actually going to start with the second equation, x plus y equals 10. So let's go 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Because if x is 0, y is 10, and if y is 0, x is 10. And so this is my first line. Now notice I did not go too far past the x or the y axis because we also know x is greater than or equal to 0, so we're going to be to the right of the y-axis. Y is greater than 0, so we're going to be above the x-axis. Okay? X plus y is less than 10, less than, so we know we're shading below that line. Now the top line, if x is 0, y is 2, so here's my 2. Okay. Let's pick another value for x. Here's 2. If x is 2, I have negative 3 times 2 plus y equals 2. So that's going to be y equals 8. So that would be way up here already. So here's this. I guess it's about here. So here's this line here. Okay. And now notice that we're above that line. So this is our feasible region. So what we're going to do next is we want to find our corner points. This is the point 0, 2. This is the point 0, 10. And then to find this point, we need to find the point where those two lines intersect. We've done all of this before. We're solving a system, solve it using any of the methods we've explored or studied in the past. Negative 3x plus y equals 2. X plus y equals 10. I'm going to multiply this equation by a negative. So we have 3x minus y equals negative 2. X plus y equals 10. When we add these two equations together, 4x equals 8, so x equals 2. So my y value here is 2. Plug that 2 back into, let's go into that equation here. If x is 2, y is going to be 8. So that point of intersection is 2, 8. Now we did this in our previous video. We found the corner points. The extra direction here is to maximize z. So we want to find the value of z at 0, 2. We want to find the value of z at 0, 10. And we want to find the value of z at 2, 8. Now what that means is we have 6 times an x value of 0 plus 2 times a y value of 2. 6 times 0 is 0. 2 times 2 is 4. And we would get a value of 4. 0 plus 4 is 4. For 0, 10, we would have 6 times 0 because x would be 0. Y is 10, so we have 2 times 10. And so that's going to be 0 plus 20 equals 20. So we have a y value of 20. For 2, 8, we're going to have 6 times the x value of 2 plus 2 times the y value of 8. 12 plus 16 is 30. The maximum value for z is the 30, and that occurs at the point 2, 8. So 2, 8, let me squeeze this in here, 2, 8 will maximize z, and that maximum value for z is 30. So I get a maximum of 30 at the point 2, 8. Okay, so we're going to look at 3 examples here. In example 2, a game company is developing 2 new games. We have a board game and a mechanical game. Each board game takes a half an hour to manufacture, a half an hour to assemble, and a quarter of an hour to inspect and package. Each mechanical game requires 1 hour to manufacture, so a mechanical game, 1 hour to manufacture, half an hour to assemble, and half an hour to inspect and package. In a given week, notice that there are 40 hours available for manufacturing, there are 32 hours available for assembly, and 18 hours for inspection and packaging. Suppose the profit on each board game is $10 and the profit on each mechanical game is $15. How much of each game should be produced each week? So X is going to represent the board games. Y is going to represent the mechanical games. Okay? So the profit that I'm going to make is $10 for each board game plus $15 for each mechanical game. Okay? Trying to make this look like a plus. That is the optimization equation. We're going to come back to that later. Let me also fix that 15 so we don't get confused. Now the constraints here for a board game is X, mechanical game is Y. Notice that we have 40 hours available for manufacturing, 32 hours for assembly, 18 hours for inspection and packaging. Those are my 3 equations. A board game, okay, so I'm going to do one equation for manufacturing, one for assembly, and one for inspection and packaging. So for manufacturing, it's a half an hour. Let me use fractions. I was going to use a decimal. Let's use fractions. A half an hour for each board game. Okay. It's also going to be, well, let's just go this way. A board game, half an hour to manufacture, a half an hour to assemble and package, and a quarter of an hour for inspection. So again, half an hour to manufacture, half an hour to assemble, quarter of an hour to inspect and package. That's all for the board game. For the mechanical game, it's 1 hour to manufacture, right? 1 hour to manufacture, half an hour to assemble, and a half an hour to inspect and package. I'm going to have less than or equal to, because notice for manufacturing, there are 40 hours. I may not use all 40 hours available from each of my employees. We have 32 or up to 32 hours available for assembly, and we have 18 or up to 18 hours available for inspection and packaging. Also, X has got to be greater than or equal to 0. Y has got to be greater than or equal to 0 because I cannot make fewer than 0 games. Next thing I want to do is I want to rewrite these equations or these inequalities without the fractions. So I'm going to multiply the first equation by 2, the second equation by 2, and the third equation by 4. So my three equations will become x plus 2y is less than or equal to 80. X plus y is less than or equal to 64. X plus 2y is less than or equal to 18 times 4 should be 72. And then again, x and y are both greater than or equal to 0. So these are my constraints. These are what I'm going to graph. So, like I've done a few times before, I don't need the second, third, or fourth quadrant. Quick inspection, I'm going to need an x value that goes as high as 80. So here's 80. I went by tens. 20, 40, 60, 80. Let's go by tens again. 10, 20, 30, 40, 50, 60, 70, 80. Okay. First equation, if x is 0, y is 40. And if y is 0, x is 80. So I'm going to draw my line. And I'm also going to label that is equation number 1. X plus y is equal to 64. So I've got 64 here, and I've got 64 about here. So there's that line. Now the third one, that's line number 2. For the third line, if x is 0, y is 36. And if y is 0, x is 72. And so we've got this line right here. Now my feasible region is going to be this inside here. I need to find my corner points. I have a corner point of 0, 0. I have a corner point here of 0, 36. I have a corner point here of 64, 0. And some of this is remembering, right, when I graphed these. And then I need to find this corner point. Notice that this equation number 1 winds up becoming irrelevant, and it gets eliminated by equation number 3. So this here is the intersection of lines 2 and 3. X plus y equals 64. X plus 2y equals 72. I'm simply going to multiply the top equation by a negative, so x minus x cancels. 2y minus y is y. 72 minus 64 is 8. So we have a y value here of 8. Then to find x, well, x plus y equals 64, so x would be 56. Okay. Now what we need to do here is go back to our profit equation. We need to find the profit for each 4 of those corner points. So I need to find the profit for 0, 0. I need to find the profit for 0, 36. I need to find the profit for 64, 0. And I need to find the profit for 56, 8. So I need to solve this equation 4 times. 10 times 0 plus 15 times 0. 10 times 0 plus 15 times 36. So again, I'm putting 0 and 36 in for x and y into that optimization equation. 10 times 64 plus 15 times 0. 10 times 56 plus 15 times 8. So I need to do all 4 of those. Again, looking at this optimization equation, putting each of those 4 points in there. So I need to do all of these calculations. 10 times 0 plus 15, so 10 times 0 plus 15 times 0. Pretty ridiculous, right? That's going to be That's going to be 0. Then we have 10 times 0 plus 15 times 36. We have 540. 10 times 64 plus 15 times 0 is going to be 640. And then we have 10 times 56 plus 15 times 8 is 680. 680 is the maximum. What was the question? How many of each board game should be produced each week for maximum profit? So each week, for maximum profit, I should make 56 board games and 8 mechanical games for a profit of $680. And there's my maximum. Okay? Like I said, I have 2 more examples that we can walk through. The Podunk Institute of Technology's math department offers 2 courses, finite math and applied calculus. So X is going to represent the finite math and Y is going to represent the applied calculus. Each section of finite math has 60 students. Each section of applied calculus has 50 students. So I'm going to talk about the number of students. Okay, there are 50 students for applied math, and each section of finite math, which is X, each section of finite math has 60 students. Each section of applied calculus has 50. The department is also allowed to offer a total of 110 sections. There's going to be X sections of finite math and Y sections of applied calculus. Furthermore, no more than 6,000 students want to take a math class. The number of sections, the department is allowed to offer a total of up to 110 sections. So X plus Y has got to be less than 110 sections. Students per section, 60 students per section of finite math, 50 students per section of applied calculus has got to be less than or equal to the total of 6,000 students. Okay. Also, X, the number of sections of finite math, must be greater than or equal to 0. Y, the number of sections of applied calculus, must be greater than or equal to 0. Okay, so let's graph this. X and Y are both equal to 0, so I don't need the second, third, or fourth quadrants. The first equation, if X is 0, Y is going to be 6,000 divided by 50 would be 120. So we have an x-intercept of 120. So let's say that that's going to be 60. 20, 40, 60, 80, 100, 120. So let's do the same thing here. 20, 40, 60, 80, 100, 120. And so if Y is 0, X is going to be 100. And so this is my first line. X plus Y has got to be less than or equal to 10. So if X is 0, Y is 110. If Y is 0, X is 110. And here's the second line. Now my picture's really bad. There's only one point in here where they're overlapping. Okay, so my feasible region is bounded by 0, 0, 0, 110, 100, 0, and then this point, which is the intersection of 60x plus 50y equals 6,000, and x plus y equals 110. First thing I would do is divide the top equation by 10. 6x plus 5y equals 600. And I would multiply the bottom equation by -5. So I have -5x minus 5y equals -550. So x equals 50. If x equals 50 and x plus y is 110, then y would be 60. So this would be the point 50, 60. So I have my 4 points. Now, suppose the university makes a profit of $100,000 on each section of finite math and $50,000 on each section of applied calculus. So my profit is, and I'm going to work in hundreds of thousands of dollars. So $100,000 for each section of finite math and $50,000 for each section of applied calculus. So there is my optimization equation. So I want to find my profit at the corner point 0, 0. I want to find my profit at the corner point 0, 110. I want to find my profit at the corner point 100, 0. And I want to find my profit at their corner point 50, 60. So again, I'm going to do all those calculations. So I have 100 times 0 plus 50 times 0 would be 0. I don't have to do that math. 100 times 0 plus 50 times 110. Let's just go ahead and do that. 50 times 110. 5,500. Then I have 100 times 100 plus 50 times 0 is 100 times 100. That would be 10,000. And then we have 100 times 50 plus 50 times 60. 100 times 50 plus 50 times 60 is 8,800. So actually, the company will make, the school will make the most money when I offer 100 sections of finite math and no sections of applied calculus. That's what and that's my optimization. Okay, we're going to look at one more equation. This one's my favorite of the three, so hopefully you've stuck around to see this. A small company makes two different kinds of kayaks, a larger model and a smaller model. The larger model I'm going to call X. The smaller model I'm going to call Y. The larger model requires 2 hours for, again, we have manufacturing, assembly, and packaging. The larger model takes 2 hours for manufacturing, 2 hours for assembly, and 3 hours for packaging. So we've got the manufacturing, assembling, and packaging. 2 hours for each X canoe, 2 hours for each X canoe to assemble, 3 hours to package each X canoe. The smaller model, or Y, takes 2 hours to manufacture, 2 hours for manufacturing, 1 hour for assembly, and 2 hours for packaging. Each week, the company has up to 120 hours available for manufacturing, up to 80 hours available for assembly, and up to 132 hours available for packaging. Again, X and Y must both be greater than or equal to 0. Also, if the company makes a profit of $75 for each of the larger kayaks, and then make $60 for each of the smaller kayaks. So there's my profit equation. Now I'm going to try something. I'm going to try to pull in my Desmos here. And I'm going to do this one using Desmos. See if this screen will work side by side. Okay. So here are our constraints. I've shown you some Desmos in the past. So 2x plus 2y is less than or equal to 120. Now I think what I'm going to do is I'm going to scrunch this a bit. And then we have the second equation, 2x plus y is less than or equal to 80. And then our third equation, 3x plus 2y is less than or equal to 132. And then finally, x has got to be greater than or equal to 0. And y has to be greater than or equal to 0. And you see that feasible region is this region in here. I don't like all of the colors, so let me take this in this black. I'm going to make it orange, make it a little bit lighter. I think these, I'm going to make them both, let's go ahead and make them both purple. Okay, so in any case, you now can see this feasible region is this region here, and I'm going to be looking for the corner points. Now, again, for those of you who are taking this for Math 158, I'm going to be looking for the graph. So if you have a test coming up with me, we're going to plot those points. But I'm going to flip back and forth here with my Desmos. Okay, let me see actually if I can get this graphed on here. So I see that we've got a line that goes through 8. So the first line, okay, has a y-intercept of 60 and an x-intercept of 60. Notice my highest here, this one goes up to 80. So that might help me 10, 20, 30, 40, 50, 60, 70, 80. $20, $40, $60, $80. No, that's what I'm going to do. 10, 20, 30, 40, 50, 60, 70, 80. So here's 80, 60, 40, 20. What I like about Desmos is you get a much better picture. So this first equation, we have an x-intercept of 60 and a y. So here's the 60 for the y-intercept and 60 for the x-intercept. And so here is that first line. The second line, 2x plus y is less than or equal to 80. Notice that we have a y-intercept of 80. We have an x-intercept at 40. Okay. In our recent videos, I've shown you graphing again and again and again. Hopefully we're getting good at graphing the lines. I'm using Desmos here just to speed me up a bit. Finally, notice with the third line here, we have a y-intercept at 0.66 and an x-intercept at 44, 0. Okay, and now this line comes in. I'm drawing these freehand, so this line comes down here. Something that gets very difficult to see is, do those three lines all intersect at the same place or different places? What I love about Desmos is I can see this region here, and I can see that we have a point of intersection here and a point of intersection here. So this is my feasible region, and I want to find those boundaries. Again, let's actually go back to these lines. So notice that 60 is this boundary point here, 0, 60. And that's the only, this point here, notice shows up already. That point of intersection right here. So this point of intersection right here, we already found here is 1248. Notice that if I click on the second line, I have this. So I don't want this line because this 2040 is outside that region. I want this one here which is this one here. What do we say that was? 28, 24. So we want the point 28, 24. And then this bottom point right here, I should be able to tell is going to be 40, 0. And again, my origin is 0, 0. So those are the 5 corner points. And that's a way that I can use Desmos. Okay. I should also be able to do the algebra that we've been pursuing over the last several videos to find those points of intersection. Okay. So I should be able to find those points of intersection. Then my profit, I want to find my profit for each of those various points. We have 0, 0, 0, 600, 1248, 24, 20, I'm sorry, 28, 24, and then we have 40, 0, okay? And we have our profit equation, which is a 75x plus 60y. One more thing I want to try to show you that I could do, another way to calculate these, I'm going to go to Stat, Edit in the calculator. I'm going to clear my lists. And in my L1, I'm going to put my x values, 0, 0, 12, 28, and 40. So notice I put the x values there. And in my y list, I have 0, 600. That shouldn't be 600. That should be a 60. 60. I apologize for copying that incorrectly. So that should be 0, 60. And then 48, 24, and 0. So now what I'm going to do in L3, I put my cursor up onto the L3 and I press equal. And you'll notice here it says L3 equals, okay? And it's blinking. Now what I want to do is I want to do 75 times, and I did second 1, that says L1. So I'm going to do 75 times whatever the value is that's in L1, plus I want to do 60 times the y value, and the y values are in L2, so that was going to be second L2. And notice when I press enter, it does all 5 multiplications at the same time. 75 times 0 plus 60 times 0, we're not surprised at all that that's 0. 75 times 0 plus 60 times 60 is 3,600. 75 times 12 plus 60 times 48, according to the calculator right there, is 3780. So this is going to be 3780. 75 times 28 plus 60 times 24 is 3540. And then lastly, 75 times 40 plus 60 times 0 is 3,000. The maximum value occurs right here. So for a maximum profit of 3780, the company needs to make 28 large and 24 small kayaks. Because remember, X is the larger, Y is the smaller. So 28 large, 24 small kayaks will give a maximum maximum profit of 3780. The question is how many of each to make: 28 large, 24 small. So 3 examples, a lot of repetition. I hope this was helpful. Again, if you do find it helpful, please remember to like and subscribe. This is the end of our 3rd unit. Please make sure that you're watching these videos and preparing for our upcoming test. Thank you very much for watching.